Okay, the next panel is going to talk about life support systems. And it's no news, I know, to the people in this audience, but perhaps to our viewers, that life support system, a closed loop system, is actually the thing that's next to the rocket that's going to bring us to Mars, but it seems that we're right on the way there. Life support systems is still the thing that's hardest to make so robust that we know for sure we can send it to Mars, have people live there for a year and a half and work there, and have them back home safely, and that life support system is still working. It's one of the reasons we want to test that in an L1 or L2 position. The next panel is going to be led by McMickell, who works for Honeywell Aerospace in engineering. He's the senior project engineer. Manager, and it's funny to talk about Honeywell. I mean, Honeywell for me is my thermostat on the wall. I also know Honeywell was the one that did the sensors at all the gates and everything when Atlanta had the Olympic Games. You know, that's Honeywell too, and Honeywell is also part of space, and you know, and they're good at, you know, finicky stuff like sensors and things. So, you know, it's not surprising that they're in there. Can my panel come out? Or are they still putting a microphone on one of them? I'll take a peek. Okay. Yes. Well, like I said, the floor is now to Brett McMickell and his panel, and he will introduce the others.
Thank you, Artemis. And thank you all for sticking around and attending this session. So I'd like to begin by introducing the panelists. We'll start with Tim.
I hear you.
Till the other one comes back. So Tim Nalette is the Chief of Advanced Systems and Technology at the United Technology Aerospace Systems. And he has over 30 years of experience developing environmental control and life support systems. We also have Robyn Gatens, who is the manager for the Systems and Technology Demonstration at NASA headquarters in the ISS division of the Human Exploration Mission Directorate, and NASA's System Maturation Lead for Environmental Control and Life Support Systems. MacCallum is the Chief Technology Officer and Corporate Executive Officer for Paragon Space Development Corp, and also the Chief Technology Officer for Worldview. You heard from him this morning about the Inspiration Mars project. And Melissa Traynor just joined us. She is a research scientist at NASA's Goddard Space Flight Center, and she is currently part of the science team for the sample analysis at Mars, the SAM payload on the Curiosity rover. So earlier this week, yesterday, you heard from the Associate Administrator about the challenges facing us, facing human exploration of Mars. And life support systems was mentioned several times. So although I think I'm a little bit biased, I'd say that this is probably the most important panel. So thanks for joining. I also forgot to say, I know there's people joining us from the webcast. There's some folks from Honeywell, so hello people from webcast. Also, thank you for joining. As you can see, we've got a distinguished panel to discuss the challenges and also talk about some of the advances in life support systems. In order to meet these challenges, it really requires collaboration between the scientists and the engineers. So you're going to hear about some of the science, the environment on Mars, some recent discoveries from Curiosity and how they relate to human systems, as well as the roadmap and gaps that we have in our environmental control systems, and then some of the advances that we've made. So I'll start by letting the panelists provide some opening statements. I do want this to be a discussion. I've asked the panelists to keep their opening statements short so that we can have questions and really have a discussion. There are microphones here, so please come up and ask questions as they come up. We'll start off with Robyn. She'll go over her opening statement.
Okay, I do have some slides. Oh, that's interesting. But not too many. Good afternoon, and thank you for hanging in there for our panel this afternoon. As Brett said, you've heard life support mentioned over and over as one of the big challenges going to Mars, and I like to think of us, or I think of us often as the poster child sometimes for the challenges going forward. We do have a lot of capability right now on the International Space Station. We've had a regenerative life support system on Space Station. We're supporting 6 crew now since 2009. And we've learned a lot. It was a bit experimental when we flew it, and we've had a lot of lessons learned, obviously, with it, and there's things we'd like to improve upon, and then some capabilities that we'd like to add as we go forward. Right now, we're about a 90% closure of our water loop, but we also use quite a few expendables and quite a few spares, we're about 50% closure on our oxygen loop, again with some expendables and some things that we need to replace. So there is room for improvement. However, we do have a lot of capability. I'm going to highlight real quickly what capabilities we do have and then focus in on trying to break down. We've done a lot of work the past couple years to really trying to break down exactly what needs do we have, what gaps do we have in life support, so we can better communicate those out to our industry partners who are trying to help us fill those gaps and solve those problems as we go forward. And I can't read that at all. I should have made my slides bigger. Real quickly, in atmosphere management, we break our systems down to air, water, and waste. So in our air system, we have obviously circulation fans and filters on the space station. For conditioning the air, we remove carbon dioxide, and we can do that either open loop manner, where we vent overboard, or closed loop, where we recover that oxygen from the CO2 or partially recover it. And we remove humidity through condensing heat exchangers, and do temperature control with heat exchangers. And like I said, we recover right now about half of the oxygen from CO2 with our Sabatier process. And we supply oxygen from an oxygen generator that is a water electrolysis process with backup stored oxygen, candles on the Russian side. So we have some dissimilar redundancies. For emergency services, fire detection, smoke detector, we have currently a carbon dioxide portable fire extinguisher. We have, if we have a fire, really our only method to recover from that right now is to vent the atmosphere or vent that particular module. Fortunately, we haven't had to do that. If we have a toxic spill, the crew goes on masks. Right now it's an oxygen mask. So I'll get into what improvements we need to make there. In the area of atmosphere monitoring, we have a mass spectrometer that monitors our major gases, carbon dioxide, oxygen, nitrogen, water vapor. We have some experimental monitors right now on board for trace organics, trace volatile organics in the air. But we primarily rely on grab sample return to analyze trace constituents in the atmosphere and verify that it's safe for the crew. And pressure management, we have total pressure and partial pressure of oxygen control through a simple valve system, positive, negative pressure relief. In our water area, stored water, we can bring up water. and resupply that way. We store in tanks, collapsible bags. We use iodine for microbial control currently. On the US side, on the Russian side, they use silver. So we have dissimilar methods of biocide control right now between the two halves of the station. And we can't mix our water for that reason. For managing wastewater, we collect urine through a spin separator. We pre-treat it, and then it's recovered by our urine processor. Right now, it was designed to recover 85% of the water from urine. And due to a lesson learned on orbit where we had calcium precipitating from out sooner than we thought because of the bone loss from the crew on orbit, we could only recover about 75% of that water from urine. We're looking now at a change in our pre-treat formula so that that calcium doesn't precipitate out and we can get back up to the design point, which was 85%. We recover water from humidity condensate and the urine distillate through multifiltration, ion exchange, and catalytic oxidation in our water processor. And that process is 100% efficient, but we do use expendables that we have to replace. And our catalyst we use is kind of a high temperature catalyst. And the water that's left over after urine processing, the brine, is currently stored and disposed of. So we lose that water. For water monitoring, we have conductivity and total organic carbon sense monitors, but then for more rigorous analysis, we have to do sample return. For managing waste, really it's a gather and store kind of thing. For logistical waste, the packaging materials, managing trash, those are all just gathered and disposed of in re-entry crafts. For metabolic waste, we're relying on the Russian commode right now, and it's collected and stored and disposed of again. So the challenges when we think about life support systems between what we're used to on space station and going to Mars, and it's a huge difference. Right now we've got so many lifelines back to the Earth that it's only a 2-day transit time. We can return samples down. We can launch spares if something fails pretty easily. We can always return the crew, and if we have to, fortunately we haven't had to do that. But as we go, further out to Mars, of course, we don't have those lifelines anymore. So we need to do all our sample analysis on board. We have to have adequate robustness in our life support systems so that we can rely on them for 2-3 years without them breaking down, or plenty of spares, and then close the loop for more. So breaking down what we think we still need going forward in these specific areas. In the area of circulation, we'd like quieter fans. We get complaints from the crew about noise, and so techniques to quiet fans. Filtration, higher capacity filters, lower maintenance. We know that we're going to need to deal with surface dust when we reach Mars, and we haven't had to deal with surface dust, obviously, on space station. So we need some additional capability in that area. And for atmosphere conditioning, right now we're having issues with our sorbent material, and our CO2 removal system on station tends to break down and dust and causes failures in other valves and other components. So we need to improve the robustness of that system. We need durable desiccants to remove humidity. And right now our water save system uses quite a bit of power. More efficient ways to do the water save associated with CO2 removal is something we've identified. Our heat exchanger coatings, we could use more robust hydrophilic coatings for our heat exchangers, and cold plates. Right now, I talked about we're at 50% oxygen recovery from CO2. This is a trade that's dependent on how the architecture falls out, but right now we're thinking we probably are going to need to go to at least 75% closure of the air loop. But again, that's a trade. We can't launch that additional 25%. You can't launch a whole module worth of equipment to be able to do that. So that is definitely a consideration. For supplying oxygen, our oxygen generator works very well, but it is rather complex. We went through very rigorous safety reviews and resulting in a lot of built-in complexity to make the thing safe. It's in a big dome. We have to purge it. So we're looking now at ways we could simplify that. Simplicity equals robustness. And so if you can simplify something, there's less ways for it to break down. In addition, if we're going to do a mission with frequent EVA, we need to replenish high-pressure oxygen. Right now, our oxygen generates ambient pressure oxygen. And so we need a way to resupply high-pressure 3,000 psi oxygen for frequent EVAs, either generated at that pressure or concentrate or compress it. For emergency services, if we're going to do a small spacecraft like Orion, an asphyxiant type suppressant like CO2 will asphyxiate the crew. And so we need to switch to some non-toxic way of putting out fires. We're looking at water mist, and that's currently in development. For fire recovery, again, if we have a fire and crew has to go on masks, rather than have to vent and put the crew at risk to vent to recover the atmosphere, some sort of smoke eater device would be nice to be able to clean up resulting from a fire or toxic spill. And then fire acid gas detectors, byproducts of fire, we need sensors to do that job. In the way of monitoring, more devices that allow us to get away from sending grab samples back home and do all our monitoring on board the spacecraft is needed. We're doing some experimental monitors, like we said, but nothing that's considered operational yet. In our water area, we'd like to explore using a common biocide that doesn't require us to remove it prior to crew consumption like iodine does. So we're looking at silver. The issue with silver is that it tends to plate out on orbit, and so we need a way to replenish that in our water system to maintain sterilization. For water recovery, we would like to not only get back to the 85% recovery from urine, but even try to get that last 15% of water from the brine. Again, that's going to be a trade of how much equipment are you going to have to bring to get that 15%. But we're looking at some technologies there to recover that. And then try to reduce our expendables. We want to get away from having to swap out filters and expendables as much as possible. For monitoring water, we need a way to monitor our biocide, and also, rather than just do total organic carbon, let's try to have a monitor that we can actually identify the individual species and quantify those in water. We also need a microbial monitor. Right now, it's a rather crew-intensive process, sort of a petri dish method on board station, and we'd like to have a monitor that can be able to identify and quantify microbial species in air and water. And finally, we haven't really had to deal with this on space station, but we might be launching the system and it has to hang out, for long periods of time dormant in between uses. So how do we deal with that, particularly if it's been used by crew and it's dirty and we leave it? Stuff's going to grow. How are we going to restart that? How are we going to know it's good to go when we get back to it? So dormancy is an issue that it's kind of new and we're starting to deal with. And finally, in the area of waste management, try to reuse, repurpose, trash, at least compact it and recover resources from it as much as possible, recover water from wet trash if we can, definitely stabilize it for long duration periods of time. For metabolic waste, we're looking at a smaller, more compact commode that can be used across our architecture in all vehicles, and doesn't involve as much crew time and crew effort to deal with. And then, again, we could look at recovering resources from metabolic waste. Whether or not that trades remains to be seen, but definitely needs to be stable for long periods of time, particularly if we're going to be on the Mars surface. So I think that's my last slide.
Let's hear about the science.
All right. Okay, I'm going to take the lead from Chris Sackney and stand up so I can point to some of my graphs a little better. So, yes, I'm happy to be here and to represent sort of the science of what we've been learning with robotic exploration from Mars. Sort of think of them, I guess, as our reconnaissance team for these future human explorers. Okay, so what's the environment at Mars like? I don't have to really tell you guys this. It's dry. It's cold. It has a variable pressure. You see a diurnal cycle each day. I have a, let's see, is this a little plot showing each day you get a good diurnal cycle, and I find that interesting when you look at this with, for example, the radiation dose rate at the surface with the pressure cycle. You can see the radiation kind of come up and down as the atmospheric pressure actually comes up and down. And then there's a big seasonal component. Up to 30% of the atmosphere is CO2 migrating back and forth from the poles during seasonal changes. And so you actually get, we see huge waves in atmospheric pressure throughout the Mars year. And so that might be something to factor in for certain surface effects. Curiosity is the current mission and the one, as Brett mentioned, I'm involved in. In Gale Crater, we're actually fairly equatorial. And warm, and so far we've had balmy temperatures like 5 degrees C. Our coldest nighttime temperature experience is around -85 C. Sorry, I forgot to fill in the Fahrenheit for those of you who aren't used to C. The relative humidity can be between 20 and 120%, but it's so cold that that's really not that much water. We're talking about parts per million of water in the atmosphere. And the composition we've talked a lot about, it's mostly carbon dioxide, but again at a much lower pressure. You have up to 1,000 parts per million of carbon monoxide, and that's another species that migrates a bit throughout the year depending on where you are. It's a very high number compared to what we would be comfortable with in the air here in this room, although again at the lower pressure, the absolute amount of molecules is actually, on Mars, I would say, is kind of approaching maybe EPA limits for what's a safe inhalation of CO. We have some small amounts of argon, nitrogen, very small amounts of oxygen, possibly methane, and also Mars is a very oxidized surface and oxidizing environment. So there's things like hydrogen peroxide in the atmosphere, and I'll talk about implications for soil. I just have a couple slides. I want to talk about some of the results from Curiosity on radiation. The radiation experiment has been, I think, provided very interesting results for human exploration. Here are just some screenshots I grabbed from the main webpage. You've got looking at the dose experienced during the trip from Earth to Mars for the instrument behind the spacecraft shielding, what spacecraft shielding there was. And the main thing to see, there's a background level, of course, and then we have these solar energetic particle events, and these are not really, they're random, right? Particle events. We don't necessarily know how many we're gonna get. Here is an example of what radiation has measured on the surface. Again, some fluctuations that have to do with maybe diurnal changes and other things, and then in this example, the first 300 sols, we just had one of these big particle events. But those particle events are big drivers of, I think, the amount of radiation that's experienced. This is a nice plot the project put together showing if you factor in the dose rate and how it would affect biological tissue, the transit to Mars here, is, of course, more than you get for an equivalent time on the space station, and a lot more than things like CT scans. And then the first 500 days on Mars is about equivalent. So again, that trip, depending on what you have to pay a lot more attention. Of course, you have no atmosphere shielding you, so you have to pay a lot more attention to the shielding on that trip. And then again, this amount on the surface is very driven by whether or not you get those big particle events, I think. Okay, so then dust came up in the last panel, and I think it's going to be an important thing to look at. And so I wanted to go over just what we do and I guess do not know about the dust on Mars. Of course, the MER rovers were able to observe some cool dust storms. We know there can be very global dust storms. Here's an image of Opportunity after getting very, very dirty on the surface, and that, of course, impacts things like the solar panels. And here's an image of a global dust storm in 2001 on the right. Okay, so this is an image of the surface dust. I first want to think about like what's actually just on the ground. If you were tromping around, what would be sticking to your boots, let's say. Curiosity sampled this area. The sample we nicknamed it Rocknest. It's an aeolian fine, so a wind-blown sand drift or sand shadow. Here are the scoop marks. Here is the dust that was collected, shown in Curiosity Scoop. Here's an image of the area where it was scooped. And so from the ripple surface, there were some coarser grains on the order of about 0.5 to 1.5 millimeters, but then some finer grains around 0.25 or 250 micron sand grains on the wall and the floor. Our experience, thankfully, was that it was very dry and powdery and very easy to move through the sampling system, unlike some of the challenges that Phoenix had with getting it stuck. And this is partly, I think, because of our location on the surface. Okay, when we take that dust and we heat it up in the SAM instrument and look at the gases that evolve off, we learn a lot about what those components are. And this also gets to the question about the ISRU extraction. In the previous talk, it was mentioned that you can have up to 3% weight percent water in these samples. And here is the curve showing, with temperature on the bottom, as we heat it up, where the bulk of that water is coming off. And most of it is coming off in this region between about 100 and 400 degrees Celsius. And other things that are evolving at the same time as that water, if you just look vertical, we have down here, some of the amounts are smaller, but we're seeing some chlorine that's coming out, some HCN. There's an oxygen peak in here, which is coming from oxychlorines or perchlorates. Perchlorates are prevalent on the Mars surface, and they present a big challenge to us scientifically in finding traces of organic molecules because they are strong oxidizers. And so they're present at about 0.5 weight percent, which is not sound like a very high number, but I think in this particular paper by Lori Leshin, when she was talking about, she said that even at these small amounts, they can be very toxic to the human body, and so you want to be mindful of those. There's a lot of sulfates. We see some sulfur come off, and then we can see a lot of other chlorine species that are probably coming from the breakdown again and the chemical action of these perchlorates. Okay, so dust that's in the air, we don't have a particular atmospheric dust experiment on Curiosity, but I pulled together data from all the different Mars observations. And I think the main idea is that what you've got in normal atmospheric loading, these particles are about 1 to 2 microns. They're very small, and they sort of fall into that category of PM 2.5, very small particles that can get into the lungs and actually get into that respirative tissue. And so their small size alone, I think, presents a big challenge. When you have a dust storm, it's not entirely clear, but you're going to get some larger particles, of course, because you're able to loft a lot larger particles in the air. And I've seen a lot of people who look at this very closely talk about the particles still, though, again, finer than talcum powder. I mean, this is fine stuff, but sometimes the size can make it an extra challenge. Mars tends to be clear during northern spring and summer, and dustier during northern fall and winter. And then the global dust storms happen, let's say, on a cadence of every few years or so, but it's not entirely understood what drives those and when they're going to happen. I put some interesting things from Pathfinder. There was a magnetic experiment looking at the magnetism, and they found about 3 about 3 weight % of magnetite would explain a level of magnetism in this dust. Elemental analysis from several of the rovers gives us an idea of how many elements you have. And typical analogs of the kind of dust in the air are weathered volcanic rocks. And what's nice is the dust so far has had a very global signature. All of the samplers that go, if they just get the very easy to access dust on the surface or that's right there on the rover, there's a very sort of general composition. We think about a bulk composition of the atmospheric dust, as opposed to where you may drill, you would see different samples. And then this is my last comment about the dust. The dust, particularly if you get a good dust storm on Mars, can be sensitive to things like electrical charging, either from UV radiation or from the effects you get from dust particles of different sizes rubbing in dust storms. You can get this triboelectric effect, charging. Because of the low humidity, you can get sustained particle charging, and so instead of dissipating that charge, it can build up and you can get it is suspected, although not definitively observed, you can get discharges and arcing, which could be an issue for hardware. Adhesion to hardware is also an issue, and this was, there were some studies done for Curiosity to make sure that those samples would be transferred well, that speak a little bit to this. And I think with that, that's what I wanted to introduce.
Thank you. Tim, you want to go next?
Okay, thanks for the invitation to come and speak to you. Just for those of you that don't know much about United Technologies aerospace systems, we used to be known as Hamilton Sunstrand, and it's good for me to see a number of our hardware systems. You know, Robyn mentioned a lot of these systems are used on ISS, and specifically the ones that we looked at earlier that she had shown, the water processor and the oxygen generator, and then Sabatier that was mentioned yesterday. When we talk about development of these systems, the biggest challenge we see as technologists, or at least the folks that are really down in the basic or applied R&D levels, are not so much that the technology itself is a challenge as much as it is in this environment and in this particular business, as you know and you've heard spoken of. Is basically cost and maintenance of a budget and a program to keep these things going. We're currently looking at technologies still that we were looking at when I was hired over 30 years ago. And that's not to say there's anything wrong with that. It's just to say there hasn't been a mission need or a real drive to close the loop, perhaps, to bring those to the levels that are required to be incorporated, or in some cases, the systems, the extent of the loop closure hasn't justified developing those systems further. It's not to say that they're easy by any stretch. So when we talk about it in the R&D world, and this is not only NASA, but the DoD, and even within our company, we're always looking at the technology readiness level, or the so-called TRL. And so when we look at the systems right now on station, a number of these systems have been operational for, you know, some of them up to 15 years or 14 years. Sabatier more recently. These are probably some of the longest duration tests that we've had going with this equipment. And when we start talking about reliability, it basically serves as the database, if you will, for the longer term missions. And while a number of these systems, or at least the components, can be reused as they are, and in this particular case, I list things like the fans and the pumps and things of that sort, and the basic technologies themselves in terms of whether it be oxygen generation or CO2 removal, those systems are huge. I mean, I don't know, when I haven't gone and looked at these vehicles, but I think of these things, a single rack's like the size of your, you know, a 21 cubic foot refrigerator. So looking at that double rack, it's hard to envision getting this in a capsule with 2 or 4 people and taking it to Mars. But that's the highest TRL system that you have with the most test data. So when you start looking at those systems, they're going to have to be repackaged, re-engineered, and even though they're high TRL 9 by definition now, when those get repackaged, a lot of that evaluation is going to have to happen again. A lot more testing is going to be done. You're going to basically change flow rates potentially. You're going to readdress safety, which is going to drive other issues. You're going to require a reduction in mass more than likely on these. And all of that's actually going to drive more cost into doing even more highly engineered and probably more densely packed systems, which is going to drive issues associated with maintenance and on-orbit maintenance. I know if you go and look at the presentation last year, Greg Gentry spoke on this, and he had a lot of photos. But there was one picture in there that I thought was pretty interesting, was what was the plan for the way that the modules were supposed to look. You know, they were nice and clean, and there were, you know, the four surfaces, no hardware, no wires protruding. And then you have what's really going on in terms of a recent picture, and there's stuff all over the place. And for these missions, when we talk about you know, having to make these things more compact, then obviously all of that, all of those issues relative to maintenance are going to be a significant or require a significant amount of effort. And those are the high TRL. So this is the stuff that currently exists and is flying. Relative to the low TRL stuff, and Robyn mentioned a lot more details, and even down to the component levels, things like hydrophilic coatings and all of the things that are kind of like incremental improvements. But if you look beyond the loop closure for oxygen now, which is at about 50%, and you start talking about having to recover more oxygen and basically recover more water in this particular case. So she mentioned the urine processor assembly is currently operating around 74, 75%. You know, that's one area which it appears with some basic chemistry change should be able to operate at the higher levels that it was originally designed for. Another area is water recovery from brine. There was a technical interchange meeting earlier in the year that NASA held that discussed these, and you know, basically doing a survey of what's going on in the R&D community. But these systems haven't been worked aggressively, I'll say, at a prototype system level for probably, you know, on the order of 20 years. And so there's the basic, you know, just the demonstration. There's the need to do microgravity testing of those systems, and then the maintenance associated with those. Those are all things that have to be worked out. And in that particular area, when you're dealing with water recovery from brine, you've got some nasty materials and just the handling of those when you start changing out things like wicks in a very closed environment, which there may be other odor problems already existing, so maybe it would be perceived as a perfume or something, I'm not sure. But and then there's additional recovery relative to oxygen recovery beyond Sabatier, and there's a number of technologies. Again, these are basically very complicated, and a lot of material handling issues, a lot of logistics, high temperature, which are going to drive a bunch of safety issues, and which are going to be aggravated in a very tight environment. And what I didn't list here, which is probably one of the bigger areas, is the stabilization and handling of waste over this duration. It's an area that typically hasn't had to be done for long periods of time. It's disposed of. It's kind of convenient right now. But for a long-term mission, it would become a very critical issue. Robyn also mentioned post-fire cleanup. In this particular area, this is not a difficult technology. It's probably more difficult defining what kind of fire event you want to handle because it's going to drive how you design the system. How many of these events do you want to plan for? is going to affect the logistics of the mission in that particular technology. So another thing I thought I would mention, and this probably results from you know, the last few years where from a industrial perspective it seems, and it's specifically in an R&D environment that I live in, where things are in flux a lot. This has the starting and stopping has a major impact to the execution of the program. So one of the big issues is obviously decide what the requirements are. These are basically, in this particular slide, are basically the comments that I got from a couple of program managers that have to deal with actually executing and meeting contract deliverables and things of that sort. Basically, get some requirements up front, decide what they are, decide what we really need, and do something with the nice-to-have stuff, either delete them or put them off as nice-to-have, but not necessarily requirements. Identify a real mission, realistic time frame, and then fund it accordingly or appropriately. There's a lot of discussion, and it's good to hear now about sustained budgets going forward, and that sort of thing is really important. In the most recent round of stops and starts, you know, there's been a number of folks. You know, the shuttle crews retired, a lot of them. The folks that were doing ECLSS that came up in this back in the shuttle days, the folks that did the early design and development of the PLIS components, many, if not most of these that were the pioneers, I'll say, in developing these technologies are gone. They're not in the business anymore. So developing those critical skills. When I hire a guy in my group with a chemical engineering degree, I don't get, you know, the latest CO2 technology out of them in the next year or two. I mean, it takes years and years for folks to become experts. And it's really important if we want to be efficient in developing these systems going forward that we maintain these critical skills. And then, of course, as a hardware guy in development, we always like more hardware. I don't like to do the analysis I did in school. I'm not good at it anymore. It's a lot easier to test the hardware and actually get your hands on it. And that's really where you get the lessons learned and really understand, because you're required to dig into what's going wrong here. And then I guess to wind up, this is my last slide, you know, what do we have now that we haven't had prior to this point in this business here? And that's really this unprecedented resource, the ISS. And we have at least another 10 years now. There's a lot of discussion. There's been some, I guess they were NRAs that had come out a year or so ago. There's a lot of requests for ideas for using the ISS as a test bed. This is something that we really need to maximize. As I said, these systems that have been up there now operating 15 years, we're still learning stuff today. The water processor in the last, probably been 2 or 3 years now, has this, you know, there's these things called siloxanes. They're big polymeric, greasy-like silicone-based compounds. It wasn't even on the radar. And all of a sudden, this is now rippling through the entire system. So it affects the hydrophilic coating in the heat exchangers, which affects the hydrophilic coating's performance. Then it breaks through. It's believed to get hydrolyzed. The higher molecular weight compounds get hydrolyzed on the surface of the heat exchanger, end up as what's called DSMD, ends up into the aqueous phase in the water processor, puts an additional load on the multi-filtration beds, overloads those, comes through, breaks through, hits the catalytic reactor, which wasn't designed to handle this. It wasn't even known. The TOC goes through, not through the roof, but the TOC goes up, and the medical doctors are concerned that the folks are drinking bad water. So, and this is what we know after operating something for 10 years. So, you know, it's really important to make these systems as robust as possible going forward. And one of the best ways to do that is maximize the amount of experiments, get them into a relevant environment. which in this particular case is ideally is ISS. Another approach that we had, or I had personal experience with, and I show a couple of pictures here that I think ought to be reconsidered, and maybe this is somewheres in NASA's thinking. It's probably called something different now. I can't keep up with what they keep renaming everything all the time, but at the time, this was 10 years ago, they had this rapid technology development program that came out, and these were specifically designed to the plan was do some research, basic research, and employ academics on the team, small businesses, but the goal was to build relatively high TRL technology in a relatively short period of time. Then they were accelerated with the Bush's exploration initiative, and we delivered some hardware in 6 months. Honeywell, there were 6 teams originally. Honeywell and Hamilton were the 2 teams that continued on to deliver actual flight hardware. But those were actually done with very few requirements, at least for our program. We needed to remove CO2 and humidity, and we knew what a person puts out relatively accurately, and we basically went in, developed very high-level requirements with NASA, and they trusted us to go do this thing right, and we delivered this system, the initial one, in 6 years, and then, I don't know what it was, maybe 8 years later, somebody decided to fly it. This thing was built it had a $50 motor on it, or a $100 motor. They actually shipped that, or launched it, and it's currently doing some CO2 removal as part of a DTO, a flight experiment on the International Space Station as we speak. A relatively inexpensive approach to getting some real-time, on-orbit experience. So I guess in summary, I'd say get the requirements early, build more hardware, and do more life testing, and you only have 10 years left for the station, so you want to get going soon. Thanks.
Thanks, Dan.
I'm sorry.
I feel a bit like a baseball batter here between Brett and Robyn and Tim. I don't really have a whole lot left to say, other than to say everything Tim said was right. It's a really interesting field to be in life support, because the problems happen slowly, and it takes lots of testing to figure out and ferret out what they are. I think one of the lessons of station was that we could have done a whole lot more testing on the ground at higher fidelity and learned a lot on the ground that we ended up learning on station. I know there was budget trades at the time and the like, but it's an interesting field in that way. The biggest single contaminant we had in Biosphere 2 were these siloxanes. We had them in the air, in the water, they were in the heat exchange. A lot of these same things, and Biosphere 2 is an incredibly different, you couldn't get more radically different a life support system from the station from Biosphere 2, but still there were many parallels. In early test beds in Biosphere 2, we didn't have the same ratios of materials. Concrete was different. Biosphere 2 had a lot of concrete inside. Metals were in different ratios. And we didn't see problems that we saw later in Biosphere 2 because the test wasn't properly set up to emulate what the system was going to be. So I can't emphasize enough what Tim said about we've got to get hands on hardware and start to test. So one of the things the Inspiration Mars Foundation funded, Dennis Tito was very adamant that we really start looking at these technologies, even if it's just benchtop, just get some key technologies running in the lab, break them, let's get some experience and also see what's happened since, 10 years ago, 15 years ago, we baselined the station technology. So we decided to use as much of station-derived experience as possible and go for the 6 primary systems that we wanted to address that form an ecosystem for Inspiration Mars. So that was CO2 removal, CO2 reduction, which means get that oxygen off the carbon dioxide and be able to use it either in the form of water or oxygen for breathing. CO2 removal is simply getting it out of the air. oxygen production, and then in the water side, a primary water processor, which is essentially the last step to get drinking water, and a urine processor system. These are all great eye charts like that. I took charting lessons from Robyn, as you can tell. The trace contaminant control system, this is what takes out things like formaldehyde and benzene and all of these siloxanes and the like, is really patterned after work that was done at Marshall. In this case, we're just standing on the shoulders of the giants that really worked these systems, and what's been working on station very effectively. We had catalyst beds and activated charcoal beds, and I can't even read my own charts here, acid gas scrubbers. We tested all of these systems for just a week. We would love to do more testing. We're basically out of funds right now to do more testing, but the systems are there. CO2 removal, we used a system that is derived in its basic technology from station. It's assorbent beds using a pressure swing, but rather than having a 4-bed system, 2 beds taking the water out of the airstream and putting it back into the airstream so that we can later capture it for drinking and use, and 2 beds dealing with carbon dioxide. We used a system that's actually being tested on station that rotates collecting water and rejecting water so that the CO2 removal bed gets a dry stream of air, and then a standard pressure swing absorption system to produce a pure, relatively pure stream of carbon dioxide that we can then go reduce and get the oxygen from. And that worked very well. Obviously, it was just still a very short test and in one gravity field, but it gave us a good sense for how the state of the technology is moving forward. Reduction is using a microlith, which is essentially a state-of-the-art catalyst bed using Savatier in concept very, very similar to what's on station. We had great recovery rates that ran around 85%, and the system worked great. Again, only for a week, but we got really good experience with the vendor and with the system running. Oxygen production was an interesting, we looked around a lot because we wanted to do this as water electrolysis. There's a number of ways to do it, but we actually had less experience in the company with water electrolysis than other means. And it turns out that there's been a lot of development in oxygen production for the Navy in submarines, and so we used a system that is fed with water vapor rather than water as a liquid form, which helps with the multiple phase issues of separating gas and water. It was very efficient, very robust. We ran it in different pressures, and we tried to starve it, and we tried to make it do things that it wasn't going to be happy doing, and it seemed to always recover very nicely and produce hydrogen for the Savatier reactor and oxygen for a crew of 2 to breathe. To get a feel for scale, that object in the picture is about that big, and it's about that much support equipment around it, obviously running in a 1G field, but again, it gave us a really good sense for how robust systems like this are. Primary water processor was really a series of off-the-shelf ion exchange and filtration beds run with a processing pump and some control around it, a very standard water treatment system you might find for a lab or something like that. But again, we beat it up with a range of contaminants and tried to, in the short time that we used it, make it break. And we got a lot of interesting lessons from it that we could process going forward, but we could feed it not so clean water and got nice drinking water out of it. And then lastly, I think this is lastly, the urine processor was probably the farthest from having an analog on station. Rather than a distillation process from one vessel to another or using an induced gravity field to separate phases, this system uses a series of membranes, and you put the brine or the urine inside a membrane bag and essentially dry it out with warm air. You can refill the bag multiple times if you don't get it too dry, and then have all the water removed simply by putting that water vapor back into the airstream where it would be collected on a condensing heat exchanger. We're also interested in this for stabilizing waste, for getting water out of trash, taking this from just doing urine to doing a range of different water-containing things like waste is the next step. But we were getting, by weight, a 95% or better water recovery. But in that remaining 5% is mostly solid. So when you say how much of the water came out of the bag that I put into the bag, it ends up being in the 99-98% range. So almost complete water recovery, water that was vaporized out of the bag and then later condensed. So we're actually pretty excited about this one moving forward as a potential for treating brine or urine on station in a way that really contains the wastes. We did essentially these 6 major systems. We put them all in one room. We ran them all at the same time and as much as possible fed from one to the other where we could. And that's what that room of benchtop stuff looks like. Virtually none of this is flight ready, or there's certainly microgravity issues with a few that have to get taken care of with making them more complex. But it was a really good hands-on experience to get these principal systems there, work with vendors, see what the issues were. The next step, I think, in any of this is we really need to start getting ecosystems put into a chamber with people. It takes a long time to find the issues. It takes a lot of experience working with these technologies. And so the longer, as a program, we wait to start building ecosystems in closed chambers with proper human loads and working those insofar as possible like they're going to be worked together in space. That's really, I think, going to very soon become the pacing item for any deep space exploration, because we've learned this lesson on station. We actually learned it a lot on Skylab, that we have to start this early on the ground and really work through a lot of the issues. Things like carbon dioxide going through Tygon. If we'd been testing at high CO2 levels on the ground, we'd have learned that lesson. So we didn't really need to go to station to do it. So that's my big pitch is even at this level that you see in a lab, putting that level of hardware in a chamber and just getting full systems working, and then refining those systems to be more and more like the hardware you would fly in space is the fastest route to getting us a reliable life support system. We're not going to be able to make it reliable until we really understand it and have essentially beaten it up. Thank you.
All right, well, we've got plenty of time for questions if you want to come down to the microphone. To get started, I'll just say, so we talked about some of the challenges. The time frame's been set in 2030s. Can we get there? When do we have to start? You want to start?
What are you doing tomorrow? That we need to, I think we don't know what the problems are going to be until we're there. So if you say, let's just run out of timeline, I've got 20 years, say, from now. Well, I've got to be on the, integrating the spacecraft and getting it all ready, say, 5 years. I have to have a locked down design 5 years from that. So that puts me, sort of 2028, 2025 type time range. If I start from now and say, well, I'm going to take several years to figure out exactly what I want to fly, get my sort of first cut technologies down. They're not flight ready, but they're the chemistries that I want to have. I want to have to test those for at least a couple of years before I know anything about them. Then I'm going to take everything that I learned in those 2 years and take another couple of years to go figure out how to fix all the problems I just had, start another cycle. Now, I really want to start running these things longer than I have to for my flight, because that's really the only way I see how robust the system is. If I have a 2-year flight, really ought to run it for 3 years. Well, now I've got that down. I'm almost 10 years into it, and I haven't even begun to start microgravity testing. So, during that period of time, we've sent subsystems up to the station, and they're working. But, you know, now I want to test in a full module on station. It's not hard to find a timeline that says, man, let's get going.
We want, like Tabor said, we need to put our pencils down on this Mars mission in the mid-2020s, late 2020s at the latest. Plus we have station to 2024. And by the time we station end of life, we want to have tested our Mars ECLSS for at least a couple years on station.
Well, there's your timeline right there.
We've,
Right.
yeah, we've got to get going.
Yeah.
Right.
No, Robyn's right on.
I guess we have a question?
Yeah, Mike Heldon, retired aerospace engineer. Question probably for Robyn. I noticed that the food cycle was not mentioned hardly at all. And on the space station, I think we get our food from logistics vehicles coming up from the Earth, and then they take the trash from that and throw it down into the Earth's atmosphere to burn up, if I understand that correctly. So if that's the case, then how do we translate that to a settlement on Mars?
Yeah, the food is an area, the way we have divided things up, that the life support people haven't claimed ownership of, but you're right. We take up food on space station right now. It's packaged. They consume it, and then it turns into metabolic waste, and we basically throw that away right now. So yeah, there's more that we could do with that. The water in the food is another thing that's a big variable as we look at systems going forward. And that plays a big part in the life support system, is how much water you're going to get in that food. And then the resulting metabolic waste, you know, how much are we going to be able to process that realistically? So, and then the introduction of fresh food, if we bring plants into a system, is it going to be supplemental? Are we going to rely on those? Right now, our focus is kind of on the physical chemical life support systems, but we see as we get down, maybe establish a surface system on a planetary base, bringing in some of those plants into our life support system as being feasible at that point.
So would there be experiments on the station to experiment with growing food, and preferably...
There's one going up now.
Yeah.
They're
Veggies.
just, yeah, they're going to be growing some plants and actually possibly trying to process water with that system and see how, if it can clean up water as well as grow plants.
Okay, thank you.
I'm a dyed-in-the-wool plant guy. You know, 2 years in Biosphere 2, you got to love the plants, right? Grew everything I ate for 2 years, and it processed all of my oxygen for the most part. We had a bit of a problem. All of my water. You know, plants are an amazing way to process air, water, and food. When you, it's probably, I don't know, 20 years ago, 15 years ago, we would make these models. Ray Wheeler would help us crank through, and we'd figure out how long in space till you get break even and you should be having plants instead of freeze-dried food. Back then we said 6 months. And what's been happening is the technology gets better and better and better and better. And now there's really not much point in plants outside of freshies and a bit and the like in space, the microgravity issues. So you say, okay, well, I'm going to have my biosphere, my bioregenerative system on Mars. So then you do the analysis that says, well, I got to have, you know, volume to grow the food. I got to have power to get the light system. I got to get light in. I have to have redundancy in case there's a radiation event or there's, you know, a leakage. So I have to have a physical chemical backup to that system. And I have to have the manpower to keep running it. It turns out that surface stays of less than 15, 20 years don't make sense for bioregenerative when you put in all the contingencies of redundancy that you need. And I think, you know, in the beginning we probably had oversimplified analysis, and then physical chemical technologies has gotten better and better. But one of the huge differences between the Inspiration Mars model of a life support system and current NASA modeling was the consumables. I mean, we had to say this is an incredibly austere mission. We are bulk packaging freeze-dried food. They're not going for the dinners. Like, the service is going to be crap. But when you look at the weight of individually prepackaged meals and individual wipes and individual hygiene items, and you stack those up, it's a huge consumable burden. And so it has to be an incredibly austere environment. Figure out how to reuse your hygiene cloths and wash them. A lot of sort of unpleasantness is going to occur with these early missions in order to keep that hygiene and food consumable down to a manageable mass and volume.
Thank you. Thank you.
Another question?
Yeah, I think this is mostly from Melissa. I'm really curious about you mentioned the dust particles, and especially the atmospheric dust. I think you said those are 2.5 ppm and smaller, which I think is about the size of like car exhaust, basically. So how are you guys going to go about verifying all the components that are going to go into these really critical systems with such fine particles here on our planet?
We're looking at Robyn, and I'm teasing her.
I mean, I can confirm that, yeah, the current understanding is the suspended particles are around 1 to 2 microns. They're very, very small particulates. Again, it's the kind of thing we worry about on Earth for air quality because it can be so damaging to the respiratory system, but it's also very challenging to filter out.
So gas collection systems, this is one of the great aspects of the 2020 ISRU mission, is to begin to understand how things like living in a talcum powder environment really affect some of the hardware for oxygen processing. These are really important tests and experiments to do on the surface just to get that early experience. What happened to this hardware? It's so hard even to reproduce that environment on the ground in a test chamber. That this early data, I think it's a brilliant stroke to do this early ISRU work on Mars 2020 and get some of that early data is incredibly important.
And again, to echo, the timeline is very important because these are the kinds of things that you may not notice in a short test, but it could become a real problem, a cumulative issue.
Yeah, over a period of a year, or exactly a year and a half. Okay, thanks.
Yeah. Given that the ECLSS on ISS is a 15-year-old plus technology, and given that we're not going to go to Mars till 2035, at that point it'll be 35 plus years old, notwithstanding the need to do testing and stuff right away, isn't there room for a challenge, a period of, given that you have pretty good requirements, you could set up a series of challenges and just sort of cast a wide net for some new ideas from non-traditional participants?
Yes.
If you did it quick.
Yes, we are starting to do that in a couple areas. The issue is funding, of course, for those challenges, but we have a couple solicitations out right now for oxygen recovery from CO2, to name one that. We honestly don't know how to solve that problem. Everything's low TRL, so we're casting the net wide, as you say, to have folks help us with that problem.
It's one thing to put out a little solicitation, but to, make a big splash with a challenge.
Oh, okay.
Play the DARPA Grand Challenge game.
Yeah.
Yeah, challenges work well when there's a tertiary reason to develop the system, and the investment that you have to put into the challenge and the risk you put in the investment to not win sort of pays off anyway. It gets harder and harder when you have to meet the really tight requirements that are needed for a Mars mission. And so challenges are great, but it turns out in the areas that are now problematic, and I think we've done a great job of identifying like oxygen and water and a few others, and really going early to say, okay, we need to open the gates on these so we can lock down what we're going to do going forward. It's tricky to get a challenge and then get real responses to one where you can't say, and then your other market is this.
Okay, thank you.
The issue of artificial gravity. Let's assume it was decided fairly quickly and you're going to be spinning up your spacecraft either going to or from Mars. Does that affect the design of the components of the ECLSS system versus being in 0G?
Okay, you want to take it?
Sure, absolutely. I guess probably the biggest thing, something like the water processor, where you can start going a straightforward, gravity-assisted, distillation processes. So certainly all the rotating equipment associated with phase separation, things of that sort would have a major impact on the designs. But again, you got to have the gravity field relatively quick into the mission. So in terms of on the air side, I don't think there's any real benefit, except perhaps condensing heat exchangers.
Phase separators, right. We've always figured if we design for microgravity, that's kind of our worst case. And then if we end up being able to take advantage of gravity, it could simplify some things like Tim said. It's kind of been our approach.
Is the implication then that what you use in the deep space hab will work without change on the surface, or do you need to have separate stuff in the surface hab on Mars? I mean, when you add the gravity.
I think in general you would use, yeah, it would work.
It would work. Like so, we could simplify some things about it on the surface. Get rid of our separator on the toilet, for example. But to name one.
So I got a question. Right now, do you think we have enough understanding of the atmosphere of Mars to build a life support system that we can be sure that it'll keep the humans alive? Tim?
I don't, well, I mean, the atmosphere, you've got plenty of CO2 there, so the biggest opportunity you have is to recover oxygen and perhaps not to have to drive loop closure in certain other areas to get it. And, somebody was saying yesterday, all you have to do is bring a straw. There's plenty of water, so a straw and a heater, I guess, maybe if you got to thaw it out or something. But I don't see major challenges in, from what I know, or, what has been presented.
The biggest question in my mind, using the atmosphere and taking advantage of that, like Tim said, it would be easy to get oxygen from CO2 if you can turn around and vent CO. But can we do that? Are there going to be restrictions in what we can vent? So that complicates the problem.
I think it's mostly about execution in terms of what are our planetary protection rules going to be and the like. But there's a lot of, we don't know till we try. We don't know what that environment holds for us in the way we've designed our thing. We think, yeah, it deals with the talcum powder just great. But it turns out, so again, that's why these 2020 missions is so important to begin getting that experience. If I had to arm wave right now, I'd say probably not. There's probably another layer of things we need to understand. I think we know well enough to say, well, we want to get CO2 and turn it into oxygen and get water from here. But what it takes to do that, I don't think we know well enough.
Are there particular questions you'd like? I mean, you mentioned the Mars 2020. Are there particular questions or tests that you'd like to see run? What stands out as, hey, I'd really like to see some scientific data on?
I want to know how hard it is to make oxygen on Mars.
Good one.
Okay, you've got me worried here. So you have a lot of technologies you have to develop and test and turn into flight hardware and test. And we have to depend upon a large unnamed space agency to fund it all and get it done. Maybe let's pretend we're on an episode of Shark Tank and you're all entrepreneurs and you've got a technology that you think might have an Earth-based application, make some money.
This is going to get bad.
And we're all the investors, and we want to hear your pitch. What's the features and benefits? What's the market? And how many millions or billions do we have to invest? If you care to play.
Look at me, Robyn.
Okay, Robyn.
I don't have any money.
Now I'm really worried.
We've done some exercises to try to see, okay, of the gaps we have, what do we think we need to go do to close those, and what kind of budget do we think we're going to need to get us to the point where we do have a Mars ECLSS operating on the space station. Not starting from scratch, starting from what we have, evolving things. But then next generation, based on those, and it's about a $500 million bill.
Depends on how the approach that we take too. I mean, we talked about Inspiration Mars, and the requirements for ECLSS for that are different than a permanent settlement on Mars. So I think that the approach and using the incremental approach, I think, will help with that. We start off with ISS and then build up the technology, cislunar. But it really, I think, depends on the approach. Fundamentally, though, I mean, there's some questions that need to be answered, but you haven't heard of any, I think, breaks. There's no magic that has to happen. I think we kind of know a direction. It's just a matter of moving forward.
Well, I think for life support, you could make the argument that we're going to get to the surface of Mars and we're going to behave sort of like we're in the space station. We don't depend on the environment. And that gets sort of problematic pretty quick, especially when you try to figure out how do I make the fuel to get back off Mars? How much mass do I have to land on Mars? And then we start looking at the amount of mass you have to land on Mars, and we only know how to do it in 1-ton increments right now. It gets harder and harder to build a scenario that's credible that doesn't have some component of ISRU in it, where we're making oxygen and fuel and like that, because we're down in the bottom of this gravity well again. And I wanted to bring as little as I can down because it's so hard to get it onto the surface. And then I want to take as little as I can to get back out. So the gravity well of Mars starts to drive you to these ISRU scenarios. And that's probably the trickier part. So we have to conquer life support just to get there, operate in orbit, get down to the ground. But then there's this thing of how do we get back out of the gravity well. When that factors in, it gets much more complicated.
Answering some of the questions, we were having a discussion about the water, and can we really just put a straw in and drink the water? Melissa, you want to talk about, you mentioned the perchlorate.
Sure. So the water that we've seen from the sampling that we've done, either with the fines on the surface or from drilling, the weight percentage translates to something like 2 pints of water for a cubic foot of soil, which sounds, refreshing, I guess. But part of the challenges is, as I've mentioned, we know that the surface of Mars is full of these perchlorates. And Phoenix saw them in a polar location. We're seeing them in equatorial location, and we're expecting them to be everywhere. And I see that with 2 issues. One is whether or not when you are, let's say, heating up this sample to get the water, do you have any difficulty with separating out some of the substances? And that may not be that big of a challenge, but what happens to the systems in which you're processing? What do the perchlorates do to that? So, we have a lot of lab work because we're trying to get at the science of how they're affecting our samples. We have a lot of lab work that shows that it can lead to the degradation of a lot of different materials in instrumentation, purification systems like GC columns that may be similar to filtrations. It can lead to a lot of degradation and degradation products, and so that's an issue. Then the straw issue, that's sort of assuming you're going to a polar location where you have a lot of ground ice or more subsurface ice. And I missed some of the discussion about planetary protection issues, but I know when we think of our robotic emissions, I don't know how that feeds in. What the chemistry of the ice itself, if you were going to stick a straw in it, would it be really nice pure water, or is it also going to have a lot of these kinds of chlorine oxidants? Is it going to be very briny? That's a really good question, and we haven't yet, from space it looks like water, but you can hide a lot in water spectroscopically.
Maybe another question that needs to be answered is, what is the water? What is the concentration of water? What does it look like? How pure is it?
Yeah, there's a lot of people that would love to send an ice drill
Yeah,
to the poles to figure that out for you, if we can leverage that.
If we're going to design a water processor for it, we need to know what's in it too.
Right, so we want to make our water processor so that the water processor that we learn to use on station is the water processor that we can use on Mars. When we talk about making sure the stuff we're developing now can be forwarded to Mars, we want to make sure that the oxygen production system from carbon dioxide can also be used to take carbon dioxide from Mars and make fuel out of it and oxygen on the surface. So the more we're programming even these basic ideas forward, like I know these resources are there, I want to be sure that my water purification system can handle perchlorate in sizable amounts. So we know enough to start planning forward and ensuring that we're asking, I think, the right initial starting set of questions because of all the work that's been done on Mars, which is what allows us to start really seriously for the first time thinking about ISRU and using these life support developed technologies in applications that are now ISRU, in situ resource utilization technologies.
Question?
Hi, so for most mission architectures that involve landing on the surface, there's the transit vehicle and then there's a lander, and these are separate. I mean, so there's a lot of obvious advantages to having those two ECLSS systems being the same system in terms of how much stuff you have to bring along, and just it's easier. Do you think that we would be able to use the same system for both vehicles, or would the difference in gravity and the difference in even the tiny amount of atmosphere mean that you wouldn't be able to do that?
Depends on what you're landing on the surface, how long does it need to support the crew? Because if it's a short-term lander, you don't need all the regenerative systems you would have had in your transit vehicle. Also, that's going to make it very heavy. Unless we can significantly downsize our equipment, a regenerative life support system takes up a lot of space and weighs a lot. So typically we think about a lander as being more of an open loop life support system, a simpler version of the closed loop system we might have on a transit vehicle. It could be, but commonality is important. And we do recognize that, if you're going to have life support system, and there's things we want to use that are common across the architecture no matter what. For example, our emergency response equipment all needs to be the same across the architecture.
Another issue that was brought up, I think, by almost everybody on the panel was the need for reliability or robustness. Do we attack that through the robustness of the components themselves, or are we looking at systematic approaches to attack robustness? What's going to be needed for Mars? Tim?
I guess from my perspective as a hardware guy, it's get something built and get it tested, and put some hours on it. And a lot of that can be done. A lot of the components themselves, unless there's something unique about them, certainly anything that would be considered common is not as much of an issue as something that's unique to the mission, a phase separator, or something that I'll say is a little bit less common. And then however it plays into the system, I think you really have to have it tested at a system level.
I think it's important to have the right balance between dissimilar redundancy and commonality. You can make an argument for both ways, right? If I have a common cause failure, I don't want it to wipe out my entire life support system. I'd rather have a dissimilar backup. On the other hand, I can take less spares. If I've got a common system, I can take one spare for multiple versions of the system. So I think finding that balance is going to be a bit of a conundrum. But
what about the combination of the systems? I mean, right now there's more federated approach, right? You have CO2 removal and cooling. Combining those has obvious weight and power savings.
Exactly.
But then your risk goes up for the system. Is that something that concerns you?
Yeah, I mean, we've had approaches we've looked at in the past where our CO2 system might be dependent on our oxygen generation system, and that was a con. We didn't want, because you don't want your oxygen generation system to go down, your CO2 removal system to go down as well. So again, we have to weigh those things, and then do I want to close my loop, or do I want to bring up and build in more complexity to do that, or would I rather bring just the extra consumables and make it simpler. So these are all factors.
One of the trades that we found ourselves thinking about a lot with Inspiration Mars was how complex are you willing to handle, or how simple are you willing to handle in exchange for operational complexity and crew dependency? So I can, and if you look at station, the optimization was clearly we need the crew members to be doing science, If you look at a transit of Mars, maybe I'm willing to spend a lot more time having the crew members service the systems, maintain the systems, change their functional modes. So there's certainly a simplicity combination with operational complexity. And I think what we're going to find ourselves going to, our hope is that we go to much simpler systems that simply take more crew time, that a crew person has to actively reconfigure it in the event that something breaks down and I need to bring up the backup system. The backup system isn't going to come up automatically. We have rules that say, you can't require the crew to intervene in order to bring up your backup system. I think we're going to have to really examine some of those, because having the backup system require, 15 minutes of fussing about to put this new system in place could save a tremendous amount of complexity in automated valving and piping and tubing. So these are trades in terms of reliability, and where they tend to go towards is the things that have the shorter time frames. I have half an hour before I have to get my CO2 scrubber back online. That's harder to say, I'm going to require 20 minutes of work, right, to get it back online. So I'm going to have a hot standby for that. But oxygen regeneration, well, I've got 10 days of oxygen in the tank. I've probably got time to go fix that. So a lot of what Robyn brings up is exactly right. And then you figure out what's the time constant associated with that action. Okay.
We've been called. I'd like to thank the panelists for participating. I think this has been a really good discussion. And I think you'll be around afterwards if you have any questions. So thank you very much.
Thank you.